Yeah, there is a faculty meeting at 3:30. I'm going to start recording. All right, let's go.
All right. Hi, everyone. Thank you for joining us. Today's seminar speaker is Professor Matthew Hitchman, who received his bachelor's degree in 1978 and PhD in 1985 at the University of Washington. From 1986 to 1987, he was a scientist at NCAR, and then in 1988, he joined the faculty here at UW-Madison. His research interests include the stratosphere and mesoscale to large scale dynamics and transport. And with that, I'll hand it over to Professor Hitchman.
Okay, thanks, Gerald. Yes, it was Sunday, February 20th, and I woke up and I just had this feeling that maybe the winter's kind of getting over with. And so I thought I'd better check the stratospheric maps and see how the whole winter evolved. And then I thought, you know, it's been a while since we've had a department seminar. And so I thought one of the categories of a department seminar is you can raise issues just for conversation in a manner that's not like something super polished for a journal publication. So I thought I'd try this. Yeah, so now I need to like share screen. Is that right? I'll try that. And I think I want Finder. No, which one? Desktop, no. Not whiteboard. Thunderbird inbox? No.
If you share the desktop, we should see what you're seeing on your desktop.
Okay. How about this one? All right. Okay.
So I think we might just be seeing your Finder window, Matt.
How about that?
We just see the Finder window.
Oh, so I'm into a slideshow. No, that didn't work.
Oh, no, you're not sharing your whole desktop. You're just sharing the Finder window right now.
Okay. I don't really know how to do that.
When you do a share screen, it should be a desktop one.
Oh, that one. Okay.
Yeah. Yeah.
All right. Sorry.
That looks right.
Oh, all right.
So we can see the wave crashing on the beach.
Okay. How about that? Does this work?
It's opening.
All right.
There we go.
It looks, how do I get rid of the stuff off to the right and make it, let's see. Oh, if I go like this.
We don't see the people on the right-hand side.
Okay.
Only you see that. We just see your screen.
All right. Slideshow, play from the start.
Yep.
Okay, so yes, how can I close the faces because it's covering part of my screen?
I'm not sure there's a way you
that.
can do that. We don't see that though, Matt. We just see the whole PowerPoint and the faces are off the right of the screen. They're not covering up your presentation at all.
Okay. Sorry for not knowing how to do this very well. Yeah, I'm trying to get rid of this because I need to see the screen. Oh, there, I got the minus symbol going. Okay. Thanks for the introduction. Here's a sample plot, and these plots are going to be the star of this show. This one happens to be 550 Kelvin isentropic analysis of potential vorticity, and you can see an interesting figure 8 pattern, or wave number 2. I will define these terms in just a minute. Oh, to advance. Down here, there's a button. I'll try that. I feel a little bit like this polar bear. You know, I do like the snow, and although it is nice and sunny, I like both sun and snow, and I'm gonna miss shoveling, in fact. But pretty soon we'll get some flowers and the season rolls along. So here are a few focal questions. How are cold air outbreaks in Madison related to the state of the polar vortex? Why is potential vorticity larger in the polar night stratosphere? How did the Northern Hemisphere polar vortex evolve this winter? And I want to point out some interesting topologies. And then there's a kind of phenomenon that operates in the middle stratosphere, which is an interesting interaction between the Aleutian High and the polar vortex. And one of the main ingredients is that their interaction leads to sudden stratospheric warmings, which is when warm air comes out of the tropics, rich in ozone, low vorticity, high in aerosol, and goes right across the pole. Another question, what provides for vertical dynamical coupling in the Northern Annular Mode? So there's been some theoretical developments in the last 20 years that might be valuable for getting insight into this problem. And then if we have time, perhaps, what was the winter of 2013-14 like in comparison? I think it was a little different as far as its causality. Okay, so here we are. This is our climatological records in Madison. And in mid-December, we got a little colder than normal. Late December, a little bit more so. But then in late January, we got some 10 degrees below normal. And then most of the middle of February was some 10, 15 degrees colder. I think it got down to minus 18 a few times, I believe. All right, so that sort of sets the stage. Try to remember that, that mid-February was cold here in Madison. How does it relate to the polar vortex evolution? So we'll need a few preliminaries in order to really understand these maps that I'm going to show you. This is a cross-section from CFSR, which is where I've been getting this data. It's February 2013, but it looks pretty much the same. Here's the stratopause up here, near 1 hectopascal. Here's a cold pool in the polar night stratosphere at high latitudes, and then you can see the cold tropical tropopause. But what we want to do is convert this now to potential temperature coordinates. So this is the same map, but just represented in terms of theta. And theta is defined to be T times, well, proportional to the inverse pressure. So that means theta will grow exponentially with height. This is a combination, it's a statement of conservation of the sum of internal plus gravitational potential energy. That's what conserving theta is. And so if you want parcels to go up and down past a theta surface, you need to have net diabatic heating. You can also use the hydrostatic law to convert this to a nice formula for theta, depending on T e to the kappa z over h. And so theta grows exponentially with height. And then we can see in this map that d theta dz is stronger in the stratosphere, which is a measure of static stability. That's one of the factors in potential vorticity, which I'll show on the next slide. So these are the 3 levels that I chose to look at. 850 Kelvin, which is, it varies a bit. And when there's a sudden warming, it'll go up and down by 1 or 2 kilometers. But let's say it's roughly around 32 kilometers altitude and 10 hectopascals. That's this pressure coordinate over here. And then 50 hectopascals corresponds to about 550 Kelvin or 22 kilometers. So that's sort of lower mid stratosphere. This one is maybe upper mid stratosphere, where the stratopause is near 50 kilometers. And then the lowest level I picked was 450 Kelvin, near 15 kilometers or 100 hectopascals, which is still in the extratropical stratosphere. So here's just a picture of the zonal mean zonal wind from Randall in 2003, a 30 to 35 meter per second subtropical westerly jet. Here's the polar night jet increasing with height, also tilting equator with height. And there's a lot of interesting dynamics, especially in the tropical middle atmosphere, which I enjoyed working on for my thesis, but that's a different story. Now, how about that potential vorticity? You can define it this way, which is big P is 1 over rho. This says right away it's going to grow exponentially with height. So in this plot, which is average for all year, potential vorticity increases upward because of 1 over rho. D theta dz gives a little step function jump, and you go into the stratosphere, a little boost from that. And this is, so Airtail's PV is the product of the vertical distribution of mass, some measure of that, with the absolute vorticity. So F is the planetary vorticity. It has a magnitude of about 10 to the minus 4 per second. And relative vorticity zeta here is about 1/10 of that, typically speaking. And overall, this has units of about 10 to the minus 6. So people say 1 PV unit is 10 to the minus 6 kelvins meters squared per kilogram second. You can also write it in terms of, in isentropic coordinates as 1 over sigma zeta plus F, where sigma is isentropic density in not kilograms per cubic meter, but kilograms per meter squared. And then think of the vertical coordinate on the box as kelvins. That's the vertical direction. Well, what do these 2 plots say? This is a comparison of Airtail's PV and ozone. And what we have is a nice demarcation of the stratosphere at about 1 PV unit. These numbers are actually 10 times that, but so And then PV increases upward into the stratosphere. It reaches 0 at the equator because F is 0. So contours are vertically aligned, which produces an infinite gradient at the equator, but don't mind that. Air goes right through it. It's not a transport barrier. Now you also notice that these contours show an increased poleward. That's due to F. So in general, you expect PV to increase upward and increase poleward. Well, here's ozone. We know that ozone has its source in the tropical upper stratosphere, and it's transported poleward and downward all winter long. And in the lower stratosphere, there's quite a nice correlation between ozone is high at higher latitudes along with PV. So at the base of the stratosphere, you expect that there's high ozone in the polar vortex. But look up here in the middle stratosphere, say at 25, 30 kilometers, ozone increases toward the equator, but PV increases toward the pole. That's true. At the uppermost portion of the polar vortex, there isn't very much ozone in the polar vortex. All throughout the winter, through some of these chaotic transport patterns that I'll show you, there's a gradual sifting of ozone into the polar vortex until by the time you're in the base of the vortex, that's where the ozone actually is. That causes me to think of the polar vortex boundary not so much as a barrier, but a flowing processor. So this is the other camp, and I'm definitely in that camp of interpretation, because obviously ozone gets into the polar vortex. All right, so you may be interested in how do the seasonal changes in potential vorticity occur? And it's hard to find these types of diagrams. This one happens to be for July, and so the polar night is over here. But just remember the sense of this. There's cooling that increases with height. Cooling increases with height. Now, think of the normal and cover this pattern up, and now look at this over here. In the polar night, you have infrared cooling to space, which is to say d theta dt is negative. So air will tend to sink through theta surfaces by carbon dioxide radiation of infrared to space, which increases upward. And so if you just look at the first term in theta coordinates for the effects of diabatic heating, following the motion, Lagrangian motion, potential vorticity can change in time in proportional to this vertical derivative of the product, sigma q. And you might think, oh, we want to produce high PV in the polar winter night, but q is negative. How is this going to work? Well, the weighting of sigma is crucial to understand this. And it's sort of a delicate argument, but since density decreases upward exponentially, roughly, what happens is the mass sinking through the lower part of a theta slab, the lowest potential temperature contour, goes out faster than it sinks into the top. So this is called a mass concentration in a theta slab by diabatic cooling. And that allows potential vorticity to increase somewhat going into the winter season. So let's get to the heart of it, which is I'm really excited about these plots. So I'm going to show daily charts of potential vorticity, temperature, and wind speed at these three levels, 850, 550, and 450. I'll start on November 1st for the uppermost one, because 10 hectopascals is the canonical level for assessing the state of the vortex. And it was quite stable throughout November, but December, January, February were quite interesting. And if you'd like to check out these products, here's the link. And I will also show a movie of total column ozone obtained from Goddard Space Flight Center. So yeah, let's go to the videos. And I'm going to end the show briefly to do that. So we'll go through a series of, I guess, 7 folders, but they go pretty quickly. And the way I'm showing these movies is Control A and then Control O for open. And then pick the first, oops, it's over here. Pick the first one, and now we can discuss it. So here is potential vorticity in the Northern Hemisphere. It's high at highest latitudes. Here's the polar vortex. That black contour actually shows you the temperature of below 195 Kelvin. And in a few minutes, I'll show you the temperature loop for 850K surface. But you can see that November is pretty stable. I'm sorry about the numbers, quite small. It's down here by the arrow, and you can see 2020, 1109 right there. Kind of meandering around. But now getting into December, things start to get a little more interesting. Oh, here's the first hint of interaction with the tropics. Do you see this plume of orange, very low PV coming out of the tropics in the sort of Asian sector and working its way around over the Pacific? This is a very common thing. So Sid Bohill in '63 said they thought that the polar vortex is probably biased towards Siberia because of the lower boundary condition for radiative transfer. It's ice. Whereas over the Pacific Ocean, there's warm sea surface temperatures radiating heat upward, and often there's stagnant air in the Aleutian High, and it heats. So that tends to bias the polar vortex to the right, toward the Asian side of this northern hemisphere. And as a result of that, the vortex often dips into the tropics, and you can see plumes of air coming around. They'll often wrap up in the Alaskan sector, and we call that an Aleutian High building event. So these plumes of air are high in ozone, high in volcanic aerosol, low in vorticity because F is 0 from where it's starting from, so it'll wrap up anticyclonically. And it's also warm. So yeah, you can see the formation of the Aleutian High here. This is December 6th. Okay, there's Aleutian High. You can see the orange off to the left. And in a minute, I'll show you a still shot comparing different altitudes and speed and other quantities, ozone, when I'm done with these loops. So this is December 16th, one of the dates that I'll show. I guess I have the power to admit. That's all right. I'll pay attention to that for participation. Otherwise, I can't advance these. Now, getting into late December, we start to get a triangular vortex. Here comes another big pulse of air out of the Eurasian sector across toward the North Pacific, forming another aspect of the Aleutian High. And each time that happens, it displaces the polar vortex off the center, off the Arctic center. And now here, this is a difficult thing, but I don't know why they did it. There's a gap of a week now. And during this time, there's a spectacular sudden warming. You can see the beginning of it right here. It's up to you to, I don't know, maybe they wanted to retain that week for studying themselves, or I don't really know, but we don't have to worry. But there is a jump. Here we go. This is definitely a polar stratospheric warming where you have warm air and low PV and high ozone right over the pole. And it squishes the polar vortex into this sort of smiley clown shape, which renders a very unusual pattern in the jet stream at this level, as I'll show in a minute. So there's a really robust Aleutian High building event. Almost split the vortex at this level, but it starts to reform. And then how the heck do we get the polar vortex over Canada so that we can account for a possible vertical correlation with our cold air outbreak in February? Well, we have some time, and look at this. It's coming around. Oh, here comes another big surge out of the tropics. Look at that orange plume, and it does just the right thing. It nudges it toward North America like this, and then it starts to roll up and kind of retrogress westward until we get the sweet spot. This is February 12th, 13th, 14th, 15th, and at this particular time, it did coincide with cold air over Madison, didn't it? Yeah, most of the mid part of February. So these end on the 18th because I did it on the 20th, and they're up to date within a few days. All right, so that's one level. Let's go down to the next level. 550 Kelvin, so this is at 50 hectopascals. And I want to take a few minutes to look at the unusual topology at this level for mid-December. So let's go ahead. December 7th, 8th, 9th, 10th, 11th, 12th, 13th. Oh, this is sort of a triangle. Oh, this looks more like a Mobius strip. But so the way this pattern looks, it almost looks like it's a loop that you can go under and over on, but that can't be. This is all westerly going all the way around. So within this pink region, you'd have to have flow that goes near the pole and then goes down into North America and back toward the pole, but not crossing over, going this way, I suppose. Somebody should pay attention to this little separatrix here that's trying to form. So now it's more of an infinity sign. Now it's more of a G clef or an ampersand, then G clef, and then going toward a cinnamon roll. So these are canonical forms. Okay, so let's try that again. The topology of this, how does this work? You have a surge of momentum around this way, but it tends to come back into this other lobe and it strengthens it and it rolls up and re-entrains that other lobe. That's kind of complicated dynamics. I don't know of any good explanation for that. So let's keep going. This is again at 50 hectopascals. Have sort of a Rossby wave breaking pattern and a trailing PV streamer. This region is called the surf zone, where there's mixing happening. We're a little farther down, so the polar vortex does not maintain quite the same degree of coherency. In fact, there's a threatening of the split of the kind of smiley shaped vortex into two, but no, they come back together. So yeah, these vortex splitting and mergers is very interesting to me. Maybe people in the applied math department can quantify this sort of thing. So then getting into, this is late January, early February. Oh, there is a split, but watch this. It just drags it right back in and merges. Fascinating. So I started to develop I tend to think by analogy, and it seems that maybe there's a very loose analogy with a tornado where you have a very strong identifiable vortex up near the base of the cloud. And sometimes as it spindles downward, it moves all around and maybe even splits into multiple vortices. There may be a loose analogy there. Let's check out the 450K surface. All right, so this is more like 100 hectopascals in the lowest stratosphere. And what we see here is similar, but it's easier to break it up into multiple vortices when you get down toward the base of the stratosphere. Here we go, those are pretty well split. This is mid-January. Maybe almost 3 or more portions of the vortex can be separately identified, but they tend to come back together. And then in February, it migrates more toward the Hudson Bay area and re-entrains its lost partner so that it becomes more circular, but it takes a while. Well, that brings us to February 18. About some more traditional measures of sudden warmings. So we can get that by looking at just first temperature at 850 and then wind speed at 850, which I guarantee the wind speed patterns are going to be of interest. It's like, I've never looked at those before. Okay, this will just be to point out the sudden warming aspect. So this is temperature at around 30 kilometers altitude or 850 Kelvin isentrope. And you can see the cold pool. It's up above the cold pool. It's near the top, so there aren't very many PSCs forming here. But you can see the Aleutian High. It's warm. It's in yellows and orange. It kind of comes and goes according to surges that come, again, out of the kind of African Asian sector. There's the spectacular warming that dominated all of January, and then an attempted reformation of the polar vortex due to radiative processes. Here comes another surge to maintain the Aleutian High, though, at the end of January. And then back toward a more stable vortex. So, well, temperature was pretty cold and biased toward Canada in February. Maybe that's compatible with a tall, deep vortex, but I'll try to describe in a few minutes what another idea about how that works. All right. Yeah, we got to check out the Speed movie. It's interesting. Don't be distracted by the title here, which says velocity analysis. It's not, it is actually speed. So just some colors right in here where it's purple, that's 0 to 5 meters per second over the pole. And so we have this polar vortex here. On the Pacific sector, we have wind speeds of 100 meters per second, which is at 240 Kelvin. That's 1/3 of the speed of sound. So you can see the maximum in wind surrounding the vortex. But when you have a sudden warming, this is really interesting. You have actually a jet over the pole, and this meridional jet that goes right over the pole is 100 meters per second, and it's flanked in the Pacific quadrant by still air, and also in the center of the polar vortex by quite still air. And when we get into the flattened pancake shape of the vortex in January after the major warming, so here's mid-January, look at this. Okay, so this part is easy to understand. You have a ripping westerly jet around the edge of the vortex, but it does a hairpin loop, and it doesn't go over the pole. It goes just shy of the pole over Greenland, so that you have an easterly jet of 60 meters per second over Greenland. Isn't that amazing? So these hairpin turns of the polar vortex, I thought were also topologically interesting. And then it, once the polar vortex kind of reforms over Canada, it becomes more of a recognizable pattern, I guess, similar to what you'd expect for a stratospheric hurricane, but it's really the polar vortex. And last but not least, let's look at column ozone. So this is a column out. It vertically integrates high ozone in the polar vortex at low levels with low ozone in the polar vortex at high levels. It integrates vertically through that complex signal. And you can see that high ozone sometimes comes out of the tropics, like in red here. It's about 400, 450 Dobson units. The equatorial values are more like 250, 300. And there's a high correlation between ozone and anticyclones in the stratosphere. So that by the end, you can see the polar vortex starting to reform, and high ozone is found on the fringe of the vortex. It sort of flows down the edge of the vortex. And in fact, I will argue that sudden stratospheric warmings aid the process of sinking of air. All right, so I'm gonna go back to this PowerPoint slide and attempt to give some description about some ideas about how some of these things work. And this is definitely a work in progress. So first of all, a summary from NASA. Here's a typical shot of column ozone. They said polar cap ozone increased gradually and was a little bit more than normal this year. That polar cap temperature decreased initially. It was a very strong November vortex, but then we had a series of warmings, and all of January was unusually warm. And then the polar vortex area was about normal. There's an interesting paper by Marcus Rex from the 2013-2014 winter that shows that you can get as much ozone depletion in the northern hemisphere as you do in the southern hemisphere. It's just obscured by a lot of transport of ozone from the tropics by wavy processes. And here's a summary, it only starts in January, that verifies that at 10 hectopascals, yes, the temperatures were above average in January. And then the polar vortex kind of came back in more strongly in February. And then indeed, this blue dotted line is 0 meters per second. So at times over the pole, surrounding the pole at 60 north, there were easterly winds. So that's a major sudden warming, if the winds, which are normally westerly, reverse to easterly. Okay, here's, I'm going to show 3 particular snapshots. This is December 16th, 850K, 550K, 450K. It's the time of the Mobius strip / infinity period. And we have this cold pool off to the right over Siberia and a ripping jet right across the pole of 100 meters per second. And yes, there will be a test on the canonical evolution of the forms from Mobius to infinity to ampersand to G clef to cinnamon roll. Not really. January 15th, after the huge sudden warming, the polar vortex was squashed into this pancake shape. And as you go downward to 450, you can see all these multiple filaments of the remnant of the vortex as it's trying to rejoin with counterparts in the troposphere. And then February 18th, the polar vortex was reestablished, biased toward Canada. And here you can see the westerlies surrounding, or the tangential azimuthal flow in a counterclockwise sense. Well, how does that relate to the surface? This is, again, the 3 PV plots that I just showed you. Here's column ozone. And I rotated it slightly so that you can see, here's Hudson Bay. There's a trough of high ozone over Hudson Bay. And this shows thickness contours. And you can see low thicknesses over the Great Lakes on the left. And this is 850 Kelvin temperature. So you can see from the light blue, it was unusually cold here and quite cold in northern Canada. But look at this. There was also a big lobe of cold air over here in Siberia that does not seem to correlate with the position of the polar vortex over Canada at this time. So how can we have a vertical coupling? Some people argue that there's a kind of rigidity due to rotation. So if you have a rotating tank and you put in some dye and it's not rotating, then you'll get mixing like this, which is sort of 3D tropical sort of turbulent mixing. But on the right, if you have rotation, you tend to get what we call geostrophic turbulence or 2-dimensional turbulence. So these filaments are vertically aligned. And you might think of this as the Aleutian High rubbing against the stratospheric polar vortex, and you have like intercalated streamers of air from both air mass bodies interacting. Well, why would this be? You know about the classical problem of Rossby, where you throw a stone in the ocean and the ocean's rotating, and you get waves radiating away, leaving a depression in the surface, and water will try to flow down and make use of that available potential energy of just the escarpment. But as soon as it starts to move, it turns to the right and goes around and around and becomes a vortex that lasts for all time. This is geostrophic adjustment theory. So there's something to this idea. And I really like Marshall and Plum's take on this. So if you do rotating tank experiments and you have a fluid close to the pole that's more dense, say due to cooling to space, in this case it's salty water, and you have a fluid in the tropics which is lighter, in this case freshwater, or buoyant light tropical air, and you remove this partition while it's rotating, then you'll develop this sloping front, which is describable by Margu's relation in terms of the density difference, and you'll have a polar displacement. This is just polarizing warm air. That's what you expect. That's a thermally direct circulation, but it only goes so far. It stops and starts circulating around in a azimuthal counterclockwise or westerly sense. So it really is this buoyancy-driven adjustment that gives rise to the polar night jet. It's air displaced from mid-latitudes toward the pole, which it conserves angular momentum. Going closer to the rotation axis, it'll have to spin up westerly. And the opposite happens at the bottom in the Arctic cold pool, where air is sinking and spreading out. It's very dense. It's burrowing under the lighter tropospheric air equatorward of it. And if you displace it equatorward, you're going to a larger moment arm so that you'll develop easterlies. So that is true climatologically, that you have a polar vortex at 10 hectopascals and you have, roughly speaking, easterly flow in the Arctic. And it's a Lagrangian phenomenon. And in between, if you look at maybe this point right here, nothing much is happening. And so this emboldens me to think of a possible analogy with the polar vortex and surface air, where I don't know if this is true. It just seems like it might be. Sudden warmings at 10 hectopascals may be related to cold air outbreaks at the surface. And there is a weak signal in between. If you try to trace a cold air outbreak at the surface directly upward to a stratospheric polar vortex at 10 hectopascals, it sort of fades out in between. The amplitude is shaped like a vase with a very narrow neck, and then it broadens out again. So And we don't, with this type of analogy, we wouldn't really need to invoke the instantaneous correlation between a cold air outbreak in Madison and a strengthening of the polar vortex, say. It may be similar to synoptic scale cyclones, where you have a tornado outbreak or maybe some freezing rain along the warm front that may not occur at the same time as when cold air goes snowfall and boulder, that there may not be at the same time. So I think there may be an analogy here. And then this is their Marshall and Plums picture of how that works at the polar vortex and the cold pool dome with a slope. And here's another version. This is a cartoon version on A Curve of Time, celebrating Carl Gustav Rossby's career, where you have a waggly jet stream, tropical air can kind of disturb this polar vortex, and you have various quadrants where polar air can come out if the polar vortex is disturbed. A little bit about sudden warmings. This is from a paper by Conway Leovy in '85. And this shows LIMS ozone surging poleward from along 0 degrees east from January 26th to 30th in 1979. And then in February 6th, 1979, you can see ozone came right over the pole in a sudden warming, and these anticyclones are related to warming underneath it associated with this sudden warming. Well, a few more attributes of the polar vortex. Tim Dunkerton had a great insight. He said, you know, if you really want to understand the Lagrangian circulation, all you have to do is understand net radiative heating. Q over d theta dz is the vertical motion in the Lagrangian sense. It has to be, because the only way you can get air to cross potential temperature surfaces is to cool it or heat it. So this is absolutely correct. So thermally direct overturning, its Lagrangian overturning, is determined by heating and cooling patterns. But this idea works in detail. So sudden warmings are part of the process. You can have parcels wiggling around in a gravity wave pattern, or going in circles and poleward and downward in a sort of Stokes drifted, you know, planetary waves, or major events like a deep Rossby wave breaking, which we could call a hemispheric Rossby wave breaking pattern. That's a sudden warming. And these also are releasing potential energy through sloping buoyancy. And here's the interesting thing. It seems like a bit of counterintuitive statement on the outset, but why does air sink in the polar vortex? Well, it's cold and it's radiating to space, but what if you put really warm air in there? That would enhance the cooling rate greatly. So when sudden warmings go into the polar night, it's warm air and it's radiating faster to space, and so it sinks more quickly through theta surfaces. And this then supports the idea that the polar vortex edge is a kind of a flowing processor whereby ozone actually accumulates inside the base of the vortex. This is the last concept that I wanted to touch base on, because it's since about 20 years ago, with some very famous papers, this has become actually a reasonable way to forecast tropospheric weather. So in its most idealized Eurocentric point of view, in a high index NAM, you have a lot of warm air flowing into Siberia and Northern Europe. Low index NAM, higher sea level pressure over the pole, less low. And so we flow into Europe and maybe colder, which is shown here. During a low index NAM, you have maybe a stronger Icelandic low and more cold air coming into Eastern North America, and more circulation, a westward penetration of circulation around the Siberian high influencing Europe. I think this basic idea should be generalized further, however, because if you look at the high-low index NAM difference for surface air temperature, during a high index NAM, there's a cold vortex over the Arctic, and it's warm in the center parts of the mid-latitudes, well, the high mid-latitudes. And the opposite occurs when you have a low index NAM. It's warmer at the surface over the pole and colder over, say, Seattle. And they had snow all the way down to Phoenix, and it's just like pattern C in my Golden Guide to Weather that I got in 4th grade. It's so exciting to see snow on cactuses. And we've had cold air outbreaks here, and they had cold air outbreaks in January and February in Europe and Asia. So I think if you look at this as blue for cold when you have a low NAM index, this just is a general indicator of you're more likely to have cold air outbreaks. This is from Wallace and Thompson. And then the stratosphere does have its own kind of mid-level oscillator with the polar vortex Aleutian High pair, but it can also be whacked really hard from below. So if you have, these are centers of disturbance for disturbing the stratosphere, the polar vortex. If you can grow a high pressure center, a blocking high in the Gulf of Alaska, that's going to disturb the polar vortex. If you can grow a blocking high in the North Atlantic, that will disturb the polar vortex. So the right-hand side is a picture of a low index NAM situation where you get phenomena like this. Low index NAM favors cold air outbreaks in these cities, Tokyo to Juneau, by a factor of 3 or so relative to a positive NAM index, which confines the cold air to high latitudes. More frozen precipitation at these mid-latitude stations with a low index NAM. Wind speeds are higher, but that's because these are mid-latitude stations. During a high index NAM, you'll have air blowing off the Pacific and keeping the interior warm. And then perhaps most notably in the North Atlantic during a low index NAM, 225 cases of blocking high in the North Atlantic and only 1 during a high index NAM. So there's a relationship between blocking highs and disturbing the polar vortex and subsequent cold air outbreaks. This one's pretty good too. Low index NAM, -5 in Bellingham. You know, I'll call my mother and see if she's worried about how her rhododendrons are doing. So this picture is definitely a take-home picture if you haven't seen it before. Let's look at the lower one, strong vortex events. If you have weak vortex events, that's what's happening this year. So if you're up here at 30 kilometers and at some particular day, like January 15th, you notice, oh my gosh, it's a weak polar vortex. Well, chances are within a week or so, you're going to get a wobbly vortex in the troposphere with persistent occurrences of such every few weeks or so. So this time scale built in, it definitely is in the category of, we call S2S, sub-seasonal to seasonal forecasting capability. So although the stratosphere only has 10% of the mass, there's something about the polar vortex and its vertical coupling that really is helpful for long-range forecasting. I thought I'd stop here to see if you want to talk about this stuff. And I can't see my clock either. Let's see, 3:14. Okay. Yeah, I don't know if you would like to talk about what I just showed, or I could rip through the polar vortex of 2013, 2014, whatever you'd like.
I'd say keep going.
All right. All right. So you all remember this one. We lived through it. 92% ice cover on the Great Lakes. That's not the case this year. So this one was more nagging, more persistent. Here's the horrible story. In December, we had cold air outbreaks. And then in January, we had a cold air outbreak. And then all of February, and we thought finally we got out of it, but no, it came back in March. And you can even see maybe hints of that persisting into late March. My goodness. So yeah, 2013, 2014, what was going on there? This just shows an example on the 23rd of February of cold air at 850 over us. I tend to think that there's a little bit of something to do with Rossby wave dynamics, where we know from this dispersion relation that if you have a long enough Rossby wave, then it can be quasi-stationary and therefore become resonant with topography or perhaps heating anomalies. This definitely has utility, but what I showed you in the movies is more in the camp of watching the Lagrangian movement of vortices. And Alan O'Neill taught me in 1992 that it kind of can drive you crazy to look at time series of plots of the zonal mean, wave number 1 amplitude, wave number 2 amplitude, wave number 3 amplitude. You'll just get spikes where they go back and forth. And I think a Lagrangian perspective where you look at a sequence of maps is better. But well, here we go. Linear Rossby wave theory. You remember this? Nick Bond, who was a friend from mine back in Seattle, and he's articulated this quite well, and he dubbed this the blob. So there was a sea surface temperature anomaly in the North Pacific, and I suspect this had something to do with the quasi-permanence of the lobe of the polar vortex over us that made it different than this year. So yeah, this is 5th of February 2014, 3 to 3.5 centigrade, a 7 Fahrenheit temperature anomaly, well, the air above that will be warmer, and you would anticipate it would tend to develop anticyclonic flow or blocking high, and it did. There tended to amplify this particular point right here in that year, and it just kept coming back, and I think it sort of fits in with shaping the vortex into this peanut shape, sort of pushing the polar vortex away from the Alaskan sector. So let's go to this PV loop. Oh, no, wrong. I hit the wrong button. Uh-oh, it's in a print mode. Gosh dang it. No. Well, you can watch it move as I deny its printing. Sorry, that's really bad. I can't make it stop. Okay, well, maybe I can move this, and then you can look underneath it. That's all right, I'll use the OK button to advance. So much of the time, the vortex was spent in a peanut shape. If you ever try this technique, don't hit the P button. You want to hit the O button. So this is February. And right then, it seemed to correlate with the polar vortex, but no, it comes, I can't sweep it out of the way because it comes right back. Once we get to the last one, I could do it normally. I'm sorry for my, it's a good way to end a talk, just to demonstrate technological inexpertise.
I don't think it's going in order and time either, Matt.
My goodness. And I can't seem to get out of it. I'm going to shut this whole folder. No, it won't let me. Why?
You
My
should
goodness.
be force quit. Yeah.
Yeah, I found force quit. Well, that was entertaining. All right, I'm going to tape force quit on my mirror so I remember. Okay, so this was January 2014, and the lobe just was persistent over Hudson Bay, and it would kind of try to rotate, but then it would just come back, almost as if the position of an anticyclone in the troposphere in the Alaska sector sort of made a dent like that. How the ridge on the west coast in the troposphere fits in with the Aleutian High is another interesting story. Sometimes it tilts westward all the way up to 10 hectopascals, sometimes not. Looks like there was a slight split in the vortex in late February, and then it moved off of the Canadian sector in February, even though it was quite cold here, and it was cold in March. So again, not quite a one-to-one correspondence between the location of the polar vortex and where cold air outbreaks occur. Sorry about the snafu. Okay, that's all I wanted to show. Anybody have any comments or?
Could I start, Matt? 2013-14 was the second warmest year of the 73-year time series of my 850 millibar cold pool at -5.
Okay.
At the time, it broke the all-time record, and then the next year was followed by an even warmer one, and they still stand way out ahead. It's so interesting that, even within that year, there were lots of buildups of cold air. They just never got anywhere hemispherically, but they obviously did locally. And so I wonder if looking at hemispheric bursts of 850 millibar cold air might be nicely correlated with some of the stuff you're seeing at 850 Kelvin on a sort of a day-to-day or week-to-week perspective during the winter season.
I would agree with that. Sometimes there's a very nice correspondence, and you can say, oh, the vortex kind of extends all the way from the surface to almost the stratopause. But then other times, maybe similar to the way a tornado spindle can not be touching the ground right underneath it, but hit a farmhouse half a mile away. A cold air outbreak may be loosely traceable in some cases.
Yeah.
There's also the time delay. It seems like you get a sudden warming, and then maybe a week later, you'll get cold air outbreaks, but probably the precise longitudinal locations of them depends on the pre-existing structure of the tropospheric long-wave pattern.
Great
Some sort of
presentation.
interaction.
Lots of great questions there. Thanks so much.
Yeah, it was fun. Thanks for listening.
Matt, this is Brad.
Yeah.
I have a couple questions and comments. So on your last discussion, to me that the high pressure, the Aleutian High, a lot of times that's stronger, in the upper stratosphere. And I'm wondering whether, looking at what's going on in the North Pacific and the troposphere what might be driving the vortex is the Aleutian High, up at 1 millibar as it extends down. If I remember Lynn Harvey's kind of classical picture of things.
Yeah, I don't have her neat software where she can build up a stack of records and show, a movie, the whole evolution from top to bottom. Those are pretty neat.
But isn't that Aleutian High, isn't that even more amplified aloft?
Yes. Yeah. In our 96 paper, if you take an average of half of the days, you see a nice smooth westward tilt with height from a ridge over the west coast, smoothly tilting westward to join with the Aleutian High at 10 hectopascals. And the amplitude of it, the range in geopotential height is 2 kilometers. So comparing the center of the polar vortex over Siberia with the Aleutian High, it's a 2-kilometer tilted rotating surface. Yeah, and it's very large amplitude. But that's a climatological description, and each day is a little different.
Then my other kind of comment and question is, I don't even remember whether it was on one of the seminars recently that I heard this, but so they're doing experiments where they're basically forcing the stratosphere with analyses,
Okay.
and then looking at the response in the troposphere. That might be one way to get a better idea of what that coupling is for that seasonal to subseasonal. And then another way, I'm wondering whether the stuff that Brett Hoover and Michael Morgan are doing, where you look at adjoints, is the adjoint a strong enough tool that you could actually trace that back a week later to a stratospheric source?
I think you're right that I've watched a few of their presentations, and it seems like, it's really interesting work with tropical cyclones and mid-latitude cyclones, but that formalism probably is generalizable to, a hemispheric, deeper type of problem, such as this one.
Yeah.
To find sensitivities, both upward communication and downward, because they're definitely both happening.
Yeah, I think that'd be interesting to explore.
I got a question.
Hey, Greg.
Hi. I've been looking at this polar vortex for a while now. I think maybe you originally got me interested in it. I can't remember how. But one of the things I noticed is the interaction of the tropical UTLS with the polar vortex seems to occur. And when the tropical plumes come up to the polar vortex, tropical plume at its head has a subtropical jet stream, but the subtropical jet stream dissipates as you go up, but it brings a reverse thermal wind effect, or maybe an intensifying thermal wind effect that the polar vortex has. So the polar vortex builds with height from 20 to 35 kilometers or so because it's cold to the polar direction. The subtropical plume cools downward from that direction. So when you go in, when the subtropical plume comes in, it comes in between the low levels and this upper level. So the two thermal winds combined. And the effect that I see is that the polar vortex seems to drop vertically downward. At the same time, the subtropical jet plume grows upward, and they grow together, so that there's a continuum of high velocity from the polar vortex just in this one point where they intersect. But there's a continuum of high velocity from the top downward that's consistent with this intermediate thermal wind. And when that happens, it seems to cause a big effect to the extratropical atmosphere. It makes the jet stronger, and it starts to lift cold air off the ground, and all kinds of things happen with regard to the lower troposphere that is much more dramatic than you get if you just had a subtropical jet alone, a subtropical plume, or a tropical plume alone, and the polar vortex alone. When you combine them, they do couple and then project downward to the surface, and that affects the surface temperature. Is there any conventional theory on this? I mean, I just see it happening, and it's obvious that it's happening, but I haven't ever heard of it being discussed in literature explicitly in that sense.
Well, I think you might be onto something somewhat new, and I've learned over time that when you say something that sort of is an intuition that you get from looking at film loops, that often you're onto something new. I must say, I personally liked your talk the best in our flash talks. That was a good one. A couple of elements. I think when people say that there's an amplification of the North Atlantic high, that's caused by what you're talking about. So you have a poleward surge of tropical air that's got low values of F. It'll roll up anticyclonically, and so it does hit the base of the stratospheric vortex if that happens. Another comment is that the poleward motion is a maximum near the tropopause. And so if you have a pre-existing stratospheric bowl shape, like on a potter's wheel, and you put your hand in the middle of it, you're going to create a vase shape and sort of pinching off. That actually is a fundamental way of creating the classic meridional slice of a tropopause fold without any circulation.
Yeah, well, I don't know if
that's a different talk, but I'll give it.
To what extent? I think this actually, you might be right. It might actually enhance the effect of tropopause folding in the lower part of the atmosphere. In fact, I know it enhances the so-called polar jet down lower. But what I see happening is this continuum, the actual thermal wind merger, the merger of the thermal baroclinic fields from low levels upward. In other words, from levels of about 12 kilometers above the ground, all the way up to levels about 30 kilometers above the ground. The baroclinic zones tend to merge so that you get a continuous lowering of temperature to the poleward direction all the way down, which enhances the strength of the jet stream in the troposphere, as well as the strength of the polar vortex aloft in those regions. And then that asymmetry that's created creates ageostrophic motions that cause up and downward motions, and a lot of weather happens because of that.
Well, all this stuff really would be great to talk about in Weather Watch, like every 15 minutes every time for a while or something, to try to sort out what's happening. It'd be fun. I would have shown this in Weather Watch, but I realized I got overly enthusiastic and accumulating too many slides, and it wouldn't fit. So
yeah,
I tried this.
But I think there's I think what you're saying is right, that there is an effect, even though it's only 10 millibars of mass
Yeah,
up in the stratosphere, it has a disproportionately strong effect
somehow.
down low. I mean, it kind of orchestrates a lot of movements that occur.
There's this idea of a Taylor column also, but I can't quite translate flow around a puck at the bottom of water, creating an anticyclone above it in a westerly flow, to how anticyclones might disturb the polar vortex, but there might be something to that.
But a Taylor column is very barotropic, right?
Yeah.
Isn't it? I mean, isn't it more just a dynamic vorticity effect rather than?
Yeah, I think it's an example of Kelvin's circulation theorem.
It could be. That's beyond me. Yeah. Well, we can talk about it.
Okay. Yeah, I lost my control of how I can't see people or anything. I'm sorry for my ineptness with with this, but I guess we have a faculty meeting now.
Yes, we do.
So yeah, I don't even know how to sign off.
All right, thanks, Matt.
Oh, here we go.